hand is peeling, and I don't know why.
I sunburnt the heck out of my back, and I'm getting like a whole new back. It's disgusting.
Yeah, once I got sunburned so bad that I was like vomiting and needing to take showers. And
That's not good. That's like heat stroke, not just sunburn.
it was pretty bad. And my back was like shedding so bad that it itched.
Oh my gosh, the itch is awful.
Yeah, and I was like, but then after I was itching it using like a bed or something, like just
There's just like
sitting around on a
skin.
bed, it caused pain, like a stabbing pain that was like excruciating.
Yeah, I believe it.
And it's the worst experience like ever.
That sounds awful.
So don't get sunburn that bad. Drink water.
Yep.
Are you honest with Oh, you manage it. Okay. Did you swim or dive in high school?
So I do the coaches.
Swim and dive? Swim? Okay. I was a swimmer in high school.
It's a big thing. I didn't realize so many people did it. I always heard from random people.
What state? Florida. I think I only had like one in Florida, like national. I did, yes.
That was the whole premise of the conversation. Sam joined a little late.
Sorry.
Well,
That's what I get for including myself in
did
conversation.
you swim? What events did you do?
I was sprinter freestyle.
Hey, freestyle sprinter. What was your 50 time?
21.6
Meters or yards?
yards.
Yards.
Course yards. Meters was 24.8, I think.
Okay.
Long course.
I think I got to short course like 7.
I have trouble tracking girls' times. I
Yeah.
felt like when I was younger, they were so similar. Then guys said puberty, girls and puberty, and you just take off, and I had trouble tracking. So girls would be like, on this, I'm like, I have no idea. I couldn't tell you. I don't even know if mine's good at this point.
I always tried to argue that I should be like given a priority time because I had to swim like 2 feet more than everyone else. I was swimming against girls that are like, I should get like a handicap for that, right?
Come on, just take off 5 seconds. That's a fair. Like,
They should standardize it, normalize it, my height.
So they also have more weight than they
But they also have bigger muscles, like more muscle mass. So they could normalize it by height and weight. We'll make it a BMI normalization. All right, okay, we're 2 minutes past the start of class. Let's bring it together.
I mean, we're already doing it.
as much. Why not?
While I'm here, do I have Seth Young, Will McGonigal, or Chase? No? Okay. That's why I can never get the homeworks back to them. All right. Bell ringer. What do we think is the correct answer? D. Why is D correct? I hear a bunch of mumbles. Yeah, you want to answer?
Because if you're doing translational, it has to be at the center of mass.
Yes. We specifically have to choose when we're doing our translational kinetic energy of a rigid body. This little g matters. This says that the point that we care about on that rigid body is specifically the center of mass point. No other point. Okay? So all of the rest of these are correct. Yes, total kinetic energy is the sum of the translational kinetic energy plus the rotational kinetic energy, which I basically just spelled out in words, item B. So item B is also correct. And then even for a rigid body, you can only use the conservation of mechanical energy equation if and only if there are only conservative forces doing work on the system. Okay, so that same definition holds for particles as for rigid bodies. That is also true. So the only one not true was D. All right, so if you answered incorrectly, go change that now so that you get full credit. Okay, a couple of announcements. There will not be recitation tomorrow on Wednesday. I'm not too terribly worried about missing a recitation this time because you just came from an exam, and then today we're doing conservation of energy for a rigid body, which is very, 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 very similar to conservation of energy for particles. It's also very similar to work energy for rigid bodies. So there's not really all that much new about today. So there's not even all of that much to review on Wednesday. But the reason is because I am headed to Kennedy Space Center to watch the Artemis launch. I am so freaking excited. I can't even tell you. I was like the biggest space nerd when I was about 11 that I went to space camp. And I was just like demolished when they ended the shuttle program and there was just like this long period of not really doing much. I'm so psyched, y'all. I'm so excited. So what's also cool is that apparently Florida State just joined this like consortium that's like this Florida Space Research Consortium. And as a part of being a part of that group, select professors get to go see the launch in the fence at Kennedy. So not only do I get to fulfill like a life goal of seeing a launch, but I get to go in the fence and y'all. Okay, so that said, launches are obviously a little bit unpredictable. So if anything happens and I have to stay in Orlando an extra day, there is the possibility I will make Thursday's class over Zoom. Okay? If all else fails, if for any reason I can't do it on Zoom, like let's say launch window is like in the middle of the day on Thursday, I will then record Thursday's lecture and post it on YouTube for you to watch afterwards. Okay? So either way, the content on Thursday is still your responsibility, but there's the possibility it either gets moved to Zoom or gets moved to asynchronous. So please keep an eye on your Canvas announcements to know which one we're doing. Okay? If you don't hear from me, assume that I'm back in town and will be in class as normal. Questions? Okay, I'm hoping to come back with really cool pictures to show you. All right, other thing that I want to announce is project modification. So I have never actually run Module 3 before. I believe in last semesters I've only run 1, 2, and the final report. I'm realizing now that we're getting really short on time, and I actually want a little bit more time to modify the assignment for Module 3. So basically I'm cutting out a step here. Instead of being 4 factors going into your total project grade, I'm dropping it down to 3. So Module 3 will be combined with the final report. Okay, so you will only submit this report one more time, and that will be basically the very, very last day of class before exam week. Okay, so I still need to get you feedback on Module 2. I still need to modify the assignment document for Module 3. So hold tight for a little bit. There's no need to really work on the project at the current moment. But I am going to extend that due date to make sure that everybody has time. Okay? So it'll be like a third, and a third due date. Questions? The third module is going to be more design focused. So we looked at several different ways of solving the same type of problem. And then we ran an experiment, and we found out that there was a huge number of discrepancies between those two things. And either way, it was not working as intended. This design portion is going to say, okay, now you need to fix it. Figure out a couple of different ways that you could engineer a solution that fixes this thing to work as it's supposed to. Okay? So that will be the focus of module 3. All right. Alrighty. If there are no questions, we'll move on to our content.
I have a question.
Yeah.
So the goal is to just modify the original design and not make a new one? Question mark?
Yeah. So I don't want you to start from scratch and make like a gobstopper bazooka or something. I want you to like work within some constraints of what we can change. So some constraints might be, I might say, if you can't change anything about the motor and you can only change the function of the path, what would you change it to so that you reach the appropriate velocity and hit the bin? Or if you have to keep the path the same and you can only change how the motor is working, what would you do? That type of thing. But I really need to think about that carefully in my assignment statement. So I need just a little more time. Other questions? Okay. I actually wanted to show a little bit of kind of where we're at. So there's kind of 4 topics that we've been working on recently. We had particles and then rigid bodies for everything that we've done. And then we've done work energy, which was that T plus some U from 1 to 2 equals T2. And then we've done conservation of energy. I am. Thank you so much for asking. Yeah, I started early today, so I wouldn't forget. Okay, and then conservation of energy looks something like T1 plus V1 equals T2 plus V2. And so we've done work energy for particles, we've done conservation of energy for particles, we've done work energy for rigid bodies, and now we just need to finish up this last one. Okay, so that's why most of the ideas we've already covered. But just for completeness, that's what we'll talk about today. All right, so the conservation of energy equation is no different between particles and rigid bodies. It's still that T1 plus V1 equals T2 plus V2. We call this the conservation of mechanical energy. The variables stand for the exact same thing. We have kinetic energy at time 1, potential energy at time 1, kinetic energy at time 2, potential energy at time 2. The only thing that changes is all of the different things that go into filling out T1, V1, T2, and V2. Okay, so with work energy, we realized that instead of just saying 1/2 mv squared is the kinetic energy, we realized, oh, now we're a rigid body and we can both translate and rotate, so we added 1/2 mv squared plus 1/2 ig omega squared. So we did translation plus rotation. And essentially that's the only difference here. So we actually don't have any new potential energy sources. We really just have the addition of rotational kinetic energy. So really quite straightforward. So let's fill in some details here just to remind ourselves of potential sources. So for potential energy, we still have, bless you, gravitational potential energy. And we say that potential energy due to gravity is equal to the weight, or mg, whatever you want to call it, weight times, for a particle, it was height. Yep, question? Yes, sorry, I went kind of fast. For a particle, it was height. And there was only one height to worry about with a particle because a particle has only one point. What do you think it is for a rigid body? The center of gravity height, right? So if we have some height scale here, height, and we have a particle, there's only one value of height for that particle. But if we have a rigid body potato, let me draw my rigid body potato. Let's say it's a really tall rigid body potato. The question becomes, well, which height do you want? Do you want the height of this point, or the height of this point, or this point, or that point? And what you'll notice is a really good guess is the center of gravity point. Okay, so I'm going to write that the height y of point G. Height of center of mass. Okay. Elastic potential energy is no different. So if we have a spring anywhere connected to our system, then the elastic potential energy is equal to positive 1/2 Ks squared. I'm saying positive here because it's always positive. This K is the spring stiffness. Or the spring constant. And what do you think S is?
The change in length of the spring.
It's either the amount of stretch or the amount of compression, right? So that's how far are you from the free length. So okay. All right, we've been through this with work energy, so I'm going to go a little bit quicker here. Our kinetic energy sources for a rigid body are, of course, due to translation and rotation. So translational kinetic energy is 1/2 mvg squared, and rotational is 1/2 ig omega squared. Okay, the definition and what qualifies as a conservative force, that's all exactly the same as for a particle. So what are maybe some examples of non-conservative forces? Friction, that's always the best first guess. So what are some non-conservative forces? Now let's actually talk about friction for a second. So remember, the definition for us to be able to use the conservation of energy equation is that only conservative forces can be doing work. It is actually possible for there to be a non-conservative force present, but if it's not doing work, we're still allowed to use conservation of energy. So let's take a really quick look at a beautiful example of when that happens. If we have an object that is rolling without slip means that this particle that's in contact with the ground instantaneously is not moving relative to the ground. Okay? And if we have a friction force acting right on that particle of our body, but that particle is not moving, it's not displacing in the direction of the force, is that friction doing any work? It is not. Okay? So with roll without slip, specifically roll without slip. Now if this object is slipping, that particle is moving in the direction of the force or opposite the direction of the force, either way. If it's slipping, that force is doing work. But if it is specifically not slipping, then that friction force is not doing work, and we don't have to worry about the fact that that friction is a non-conservative force. That's a little bit weird, I know. It can exist, but as long as it's not doing work, we're safe. Okay, we're actually going to see that in one of our example problems today. All right, what's another non-conservative force? This one's a little more esoteric. Drag. Drag is basically air friction. So I agree with you, but we specifically never deal with drag in this class, so I'm not going to put it. Yeah, question? External forces, yeah. External forces and external torques. Okay, so now that we're talking about a rigid body, we need to add the fact that an external torque is also not necessarily conservative. Okay, that's really all you need to worry about in this class. If you see external forces or torques, don't use this one. If you see friction and you're really unsure about whether that friction is doing work, maybe don't use this one. Question?
External forces, if they don't do work, can you still use the damn thing? Or?
Beautiful. Yes. Yeah, if it's not doing work, it doesn't matter. We can use conservation of energy. So let's say I have a box, and for whatever reason, Dr. Higgins is pushing down on that box, but I'm not at all translating in that direction. Maybe it goes this way or this way. My force is not doing work. So I think I actually need to be a little bit more specific in that if there's no friction in this case. Because the normal force would then be scaling by my pushing force. That was way more complicated than I meant it to be. In general, yes. The answer is yes. Yeah. If it's not doing work, you're good. Okay, let's do examples. That's really small. Let's make it bigger. What is that movie? It's like this stupid Netflix movie. It's about a tire that's like a killer tire. Have you guys seen that? No, okay, I'm aging myself. There was the stupidest movie I have ever seen in my life that was like really big when I started undergrad. It was incredibly stupid, but I don't know why. This problem reminds me of it because it's like a tire that has a life of its own and then it... Okay, enough embarrassment, Dr. Higgins. All right, the tire has a mass of 8 kilograms, a radius of 0.3 meters, and a radius of gyration about its center of gravity g of kg equals 0.25 meters. If it is released from rest at the top of the hill, determine the velocity of its center at the bottom of the hill if it rolls without slipping. Okay, so here I'm just reminding you of the radius of gyration equation. So essentially, when they give you the radius of gyration, it's a roundabout way of giving you the mass moment of inertia.
Theo found the movie, but it's called
Rubber? Yeah, it was the stupidest movie ever. Don't waste your life on it. But it was hilarious. And how stupid it was. Okay. So, what do you think might be some of the indicators that we would like to use either work energy or conservation of energy? Leah? I wouldn't actually necessarily say that's one of the indicators. So roll without slip is just a kinematic relationship that's going to hold between the velocity of the center of gravity and the angular rotation of the thing. It really matters more what is being asked of you in the problem. So it's asking us determine the velocity of its center at the bottom of the hill. Okay, and then it tells us that we're starting from rest. So we have a change in velocity after some displacement has occurred. That is always my indicator that I should be thinking, work energy at the least. But if there's no non-conservative forces, maybe even conservation of energy. Okay, so my light bulb moment is that it's asking me about a change in velocity after some displacement has occurred. Use an energy method. Okay, and why is it that these methods are more convenient than doing equations of motion? Well, our equations of motion are all written in terms of accelerations, right? Sum of forces equals mass times acceleration. Sum of moments equals angular acceleration. If I'm not being asked about an acceleration or a force, I would probably rather use an equation that incorporates velocities. And velocities are straight there, beautifully right there in our kinetic energy part of the equation for the work energy, okay? So with work energy, we're dealing with velocities, which is exactly what the problem is asking me for. So if I recognize that, it can sometimes save me from having to do an integration, which most people like to avoid doing, okay? All right, so let's look. If I'm going to, let's consider, does this problem qualify for the conservation of energy equation? What do you think? Do we have any non-conservative forces present?
Not ones that do work.
Okay. Even if it's not doing work, are there any non-conservative forces present?
I mean, there has to be friction if it's relevant outside.
There has to be friction. Absolutely. So yes, absolutely. There is friction in this problem. Nowhere in here does it say assume a frictionless hill. Okay, it doesn't say that, so we can't assume a frictionless hill. And it's rolling without slip, so there has to be friction keeping it rolling without slip. However, we just talked about the friction for roll without slip. Does friction for roll without slip do work? No. Okay. Is that the only non-conservative force in this problem? Yes, there's no other external forces. We know that gravity is conservative. There's really nothing else here. Okay? So I'm going to put a star. Friction does not do work because the object is not slipping. So this means that the contact point is not displacing in the direction of the force. Okay, so the answer to this question is yes. Yes, we do qualify. No non-conservative forces are doing work. Okay? All right, so that means I want to set up my equation. My conservation of energy equation says T1 plus V1 equals T2 plus V2. And I want to go variable by variable. So tell me about the kinetic energy at position 1. 0. Why is it 0? Starting at rest. Beautiful. Okay, tell me about V1. Do I have any potential energy at position 1?
Yes.
Okay, due to what?
Due to gravity.
Due to gravity. That's it. Yep. So equals Vg, which is equal to mg times y of the center of mass. So remember, for gravity, we get to set our datum. So we get to set where we're measuring with respect to. And I would love for us to have 0 gravitational potential energy at time 2. So I'm going to say this is my datum. such that at time 1, I'm at a height of 4 meters. Okay, so the mass is 8. 8 times 9.81 times 4 meters. Very good. Now tell me about T2. Any kinetic energy at time 2? See some heads nodding. Yep, that's correct. There's kinetic energy. What sources?
Rotational and translational.
Yes, rotational and translational. Okay, so I've got a 1/2 mvg squared plus a 1/2 ig omega squared. Great. Let's see. I believe v. Oh, that's confusing. I'm going to call this v gravity instead of vg. And this is really a capital V to differentiate us from speed down here. Okay. All right, is there anything I can fill in here? Well, I can probably fill in the mass. That's 8 kilograms. I believe the velocity of its center at the bottom of the hill is what it's asking me for. So Vg squared, we need to find this. Okay. What about Ig? Can I find that? Yes, I need to find that using my radius of gyration. So it tells us that 0.25 equals the square root of Ig over mass. So I'm thinking 0.25 squared times 8 equals Ig. Let's plug that in. Yep. Times omega squared. I don't know how much it's spinning at time 2. Okay, let's leave it there for a moment. Whenever I see Vg and omega, and I know this thing is doing roll without slip, you should immediately think, I'm going to have to use that roll without slip equation. And you will. But let's put a pin in this really quick and we'll come back to that in a second. Okay, so let's look at potential energy at 2. Any potential energy at 2? Nope. I'm at my gravitational datum, so I have none. 0 at the gravity datum.
You set your datum one lower than the 4, like a meter down or something like that. You have to then have a potential for gravity.
Yes. It just means that I would still have some potential energy at point 2. Yep. Okay. Okay, so let's plug everything in back into our conservation of energy equation. So I have 0 plus my V1, which is 8 times 9.81 times 4, equals my T2, which is 4 times Vg squared plus 4 times 0.25 squared omega squared, and then plus 0 final potential energy. Oops. Come on. Plus 0. Okay, here's where the rubber really hits the road, where we need to, that's funny because it's tire. Here's where we need to realize we need the roll without slip equation, is because I have one equation and 2 unknowns, and that's always going to be a problem. Okay, 1 equation, 2 unknowns. Really, I would like to have 2 equations for 2 unknowns. And so where do I get that other equation? Well, I do my roll without slip equation. Okay, so problem. 1 equation, two unknowns. My two unknowns are VG and omega. So use roll without slip. So what is roll without slip? Tell me. Anyone remember that relationship?
V equals omega r.
Yep. The velocity of the center of mass G is equal to, I really shouldn't call that velocity. I should call that, I'm writing it in the scalar form. So this really should just be the speed equals omega r. Okay. And what is my radius? Does it tell me the radius of this thing? Aha, beautiful. 0.3 meters. Okay. So now I have two equations and two unknowns, and I can solve that system. Okay, so it's asking me to solve for VG, so I'm thinking I would like to get rid of omega. So if I say omega equals VG over 0.3, and then I plug that in above, what do we get? Anyone want a calculator for me? What you got?
11.11 VG or W equals what equation do you want us to solve for?
Can you find VG?
Just the final VG, I got 6.8.
Beautiful. Yep. Okay. So final VG. If we solve the system, we get VG equals 6.81 meters per second. And that's our final answer. Okay, any questions here?
Can you solve these problems using the integral method of the UF equals to the integral whatever it was? Something along those lines?
Generally, yes. Generally, yes, but what you have to be careful about is when, like, if we were to find that the acceleration of g is equal to some value at a particular time point, if we were to integrate that as like a scalar value, let's say it was like 4 meters per second squared at t equals 2 seconds, something like that, right? If we integrate that like this, we're saying that acceleration is 4 meters per second squared always. If that is true, this is fine. But if acceleration is changing over time, what we really need to integrate is that function of time, not the value at a given instant in time. Right? So like, let's say the acceleration of g as parts of doing this problem is going to be visualizing kind of the two different positions that this thing is going to be in. So what it's telling you is that we're going to pull up on this cable and until the point where we start to tip. And the point where we start to tip is the point when the center of gravity, G, is like directly over top of point C, okay, which is not the point that's shown because the center of gravity of this thing right now is slightly off to the left of C, right, because it's smack in the middle of the block. But once this thing starts tipping, we'll have something like, it'll be up on one edge, which is going to put G smack over top of C. Something like this. And after that point, once it starts to tip past that point, it's saying that, all right, we're done pulling on that rope. There's no more rope force. It's just going to fall freely after that. Okay, so I want you to think of this as basically time 1. And then time 2, actually I'm going to draw it kind of smack on top. What they're saying is that during its rotation, the corner C, that point never moves. It doesn't slip forward or backwards. So at the second point in time, I'll draw it in red to be different. That corner is still at that exact same location, C. But now this corner has hit the ground at A. Okay, so this is T equals 2. And I can draw G over here as well. Okay, one thing that you will need to know is our mass moment of inertia equation. Cut, paste. Okay. That said, I'm going to leave you here to try to take a stab at this one, okay? We have plenty of time, so take your time and try to explore this problem. So question for you, do we qualify for the conservation of energy? We got some nods. Okay. Why do you think yes?
Because the external force stops at the tipping point and friction isn't moving at all.
Beautiful. Very well described. Yeah. So between the 2 points that I care about, the external T, the external force T is gone, right? As soon as we start tipping, it says that T is no longer there. So we don't have to worry about T as an external force between time 1 and time 2. Now there is friction that is keeping point C in place, but C is not displacing in the direction of friction because it's not slipping, okay? So that friction at the corner is also not doing work. So really the only thing doing work here is gravity, which is a conservative force, so we do qualify. Tell me about T1. Any kinetic energy to start with? No, because we're starting at rest. Potential energy at time 1. We do have potential energy, but in order to see that, we have to set a datum, okay? So I'm going to set my datum at the height of the center of gravity in its final location. So this is kind of the icky part where I need to figure out how far above that datum do we start out. Okay, so we really need to know what is this change in height. Any ideas on how to do that? Leia? Yeah, so we're going to have to draw some trig, essentially. So I know that the center of this block, the center of mass of this block is going to be half the length of the block along its long edge. So that should be 1 foot, okay? And I know that it's in the center in the other direction too, which should be half of 0.5 feet. So this here is 0.25 feet. And the question is essentially, what is this purple line? How long is that purple line? Here. And then we can subtract off this little bit to change the change in height from 1 to 2. Okay, so if I draw that maybe somewhere else. Whoops. I got 1 foot, 0.25 feet, a right angle, and I want to know the hypotenuse. Well, that looks like a Pythagorean theorem to me. So a squared plus b squared equals c squared. What do we get for that c value? Okay. What do we get? 1.007 feet. Anyone else get that same value? Yeah? Okay. All right, so that's that full purple line, but the change in height, we need to subtract out the half of the small width. Okay, so we need to find the change in height is really 1.0307 minus 0.25. What do we get there?
0.7807.
Do we have agreement? Yeah, okay. Okay, So my height above the datum is this 0.78 feet. So my initial potential energy is mg y sub g, which is, my mass is, well, mg will be 150 pounds times the 0.7807. Okay, so what do we get for V1, total value? Hadassah, do you have it? Nope, okay. 17.11?
117.1.
117.1. Okay. Okay, that should be my full potential energy. All right, let's look at kinetic energy at time 2. What contributions do I have? This is kind of an interesting one. So you really want to pretend as though you're being asked about like the instant right before it hits the block. The instant right before it hits the block, does it have translational kinetic energy? Is point G going to be translating? Absolutely. Is it going to be rotating? Yes. So I will have, right before it hits the ground, I will have both translation and rotation. So I'll have 1/2 mvg squared plus 1/2 ig omega squared. Neither of those are 0 the instant before we hit the ground. Okay. Let's see. We'll need to fill in a few things. So I need to solve for IG, which I gave to you guys up here. And we'll need mass, which is 150 over 32.2. So 1/2 150 over 32.2 times VG squared plus 1/2 times IG. So 1/12 MA squared plus B squared. Half M times A squared, which is 0.5 squared, plus B squared, which is 2. Oh, I forgot the 1/12. Sorry. Times omega squared. All right, tell me about V2. Any potential energy? Nope, that's where we set our datum. Okay, let's plug everything in and see what we got. So we have 0 for T1 plus 117.11 for V1 equals 1/2 times 150 over 32.2 times VG squared plus 1/2 1/12 150 over 32.2 times 5 squared plus 2 squared omega squared. Uh-oh. I'm in the same problem I was before. I have 2 unknowns here in one equation. What do I do? I heard someone whisper something.
Roll with us.
Very, very similar. It's actually going to be the same exact equation, but we're also somewhat doing fixed axis rotation. Right, we're rotating about point C, and point C is not moving. So we're doing fixed axis rotation. So we could actually relate VG and omega using our fixed axis rotation equation. About C, which says that VG equals omega cross RG. But it is actually okay to also say that VG is equal to omega R. Okay, so what is my radius then?
Can it be one? Because actually falling into that doesn't change.
So the radius, I'm trying to relate point G, or sorry, I'm doing fixed axis rotation about C, and I'm curious about point G. So my radius is going to be this thing. Yes. Yeah, it's going to be the hypotenuse, that same hypotenuse as before. So it should be 1.0307.
Normally would the center of mass just be the radius in most cases? Unless you had to do that thing, like you just said, like if they didn't have that would make sense.
So let's pretend that this were a pendulum. If this were a pendulum and I'm thinking about a rigid body here, where this is my fixed axis of rotation and this is G, we'd have the same radius as before, right? Now, if my pendulum were like smack in the middle here, such that it was directly above G, then it would be half the length. Does that make sense?
Yeah.
Okay.
Oh, yeah, 'cause the home center.
Yeah. Okay, so now what does this tell me? I have two equations, two unknowns. That means that I can solve the system of equations. Beautiful. That's going to tell me VG and omega. Hooray! Did I solve the problem? No. It didn't ask me for VG. What did it ask me for?
The
VA. That's over here. Uh-oh. I know the velocity of G, but I want to know the velocity of A. Whatever will I do?
Parallel axis.
That's for finding mass moments of inertia.
V of A equals V of G plus V of A over G.
That's for two particles that are not on the same rigid body.
Can you do the fixed axis rotation, like the special one with like in respect to like another point?
Yes, you're talking about using the equation that relates 2 points on the same rigid body doing fixed axis rotation. Yeah. Where is that equation? I gotta find that equation. I don't have my equation sheet. That's not good. I believe it's V A equals VG plus omega cross R. A slash G. Can someone double check that on the equation sheet for me? Two points on the same rigid body?
That's for general planar motion, but yeah.
Okay. Yeah, that should still work. Okay, so let's do this. So did you guys solve for VG and omega? What'd you get for VG?
6.19.
6.19. Do. Looks like I did this a little bit differently. Did anyone else get VG equals 6.19? When you solve the system?
can't answer as close to it.
Very close to it?
Yeah.
Okay.
I got 6.15 or 6.25, depending on how you round.
And then what'd you get for omega? Great, that's what I have as well. Okay. So if we have VG and we want to know VA, I'm missing some arrows here. VA, what direction is VG going in right before it hits the ground? Straight down? I'm going to say that's going the negative J direction. So minus 6.19 J hat. And then I'm rotating clockwise, so that's going to be a negative K hat direction. So minus 5.96 K hat. Right, because omega is the same across the rigid body. Regardless of where you are on the rigid body, omega is the same. So we could also say that this VA is equal to 5.96 times 2 feet. Regardless of how you go about doing this, you should get that VA is equal to 11.9 feet per second. Okay, I want to review really quick some of the major decisions that we made. So we looked at this problem and we realized we looked at either of the problems and we realized it was asking us about a change in velocity after some displacement had occurred. That is always going to indicate to you that you should look at doing either work energy or conservation of energy because both of those equations involve velocities. So it's going to be easier for you to find a velocity, okay? So then we said, okay, well, do we even qualify for conservation of energy? Well, today's the conservation of energy day, so surprise, surprise, yes, we did qualify for conservation of energy, but we had to think very carefully about whether all the non-conservative forces were doing work or not, okay? So had to very carefully think about whether we qualified for conservation of energy. And then we used that equation to solve for a final velocity of the center of gravity. That's all well and good, but we actually wanted to know about a different point on the same rigid body. But you know that we have equations that tell us how to take what we know about one point on a rigid body and solve for the velocity happening at a different point on the same rigid body. You can do the same thing with accelerations, right? Okay? So the fact that it was asking about point A, not a problem. It just meant that you need to go hunt for that final kinematic equation. All right. Any questions on what we did today? Anything at all? Okay, I'll let you go early. Question? Before we leave, do I have Seth Young? Do I have Will McGonigal? Do I have Chase? Can Seth and Will come get homeworks from me, please? Yes, Ms. Caesar.
You're just late. But I wanted to ask why, even though there was friction,
Yes.
why was friction not doing work if it was when it was rolling without slip?
Because roll, specifically for roll without slip,
Okay.
it means that the point that is instantaneously in contact with the ground
The velocity is zero.
is zero.
Right?
So it is not going to displace in the direction of that force. Right,
But-
so this is friction working on it.
Right.
And this point is not at all going to move in that direction. Now,
Oh,
an instant away from this point is going to be over here, and friction is no longer working on it.
Right. So friction is working on that point, but not there.
Right. So, at the location where friction is applied, that particle is not
Because that's the
displacing.
point. Because that's the point of contact with
Yes.
the ground, right?
Yes.
And so there's no force because A equals 0.
There's a force. There is a force. It's just that this non-conservative force is not doing work.
Right. Okay, wait. Now I'm confused again because if force is equal to mass times acceleration,
It's
And-
wait, what? Yeah. Yeah.
Right.
Well, the sum of forces for a full rigid body is equal to mass of the whole rigid body times acceleration of point G of the rigid body.
does that not apply to individual forces as well, then?
Not unless you're talking about a particle.
Oh, I guess that's true. Yeah.
This
Never
is a
mind.
whole rigid
Never
body.
mind then. That makes sense. So
Yeah.
velocity is 0 at that point.
Yep.
If you're doing roll without slip, that's where friction acts. So friction doesn't do work
Correct.
because
Correct.
the point doesn't work.
Beautiful.
So, kind of a little bit of a stretch of a request, but
Okay, hold on. Let me stop recording.